This is a boost converter, and I will show you how to find the state space model, both with and without a changing duty cycle. So let's first look at it when the duty cycle is constant. The state space model is written as x dot is equal to ax plus bu. So x are the states that we want to measure or find. So those are the output voltage and the inductor current. And U is the input. So in this case, it is the input voltage. So I'll just put it here. Now we first want to find the matrices A and B. In order to do that, we need to look at the equations for the circuit. So there are two different types of states. So we have one when the MOSFET is on and one when it's off. So we will get two different sets of A and B. Now in both cases when it's on and off, we want to look at the equations for the capacitor and the inductor. So the change of current in the inductor over time is equal to the voltage over the inductor divided by the inductance. And for the capacitor, we have that the change of voltage over the capacitor over time is equal to the current going through the capacitor over the capacitance. The voltage over the capacitor is equal to the voltage over the output. So we can just remove the C and add an O. I just changed this V to a small v because it's time variant. First, we're going to look at the boost converter when the MOSFET is on. So when the MOSFET is on, there's just a wire here. So there is 0 voltage here, which means that the voltage over the inductor is equal to VI. So we can now substitute VL with VI in this equation. So the change of current over time is therefore equal to VI over VL. Because the MOSFET is on, the current from the inductor will just go through the MOSFET and not through the diode, which means that the sum of the current in the capacitor and on the output is equal to 0. So we have that the current in the capacitor is equal to minus the current on the output. And the current on the output is equal to the output voltage over R. So we can put this into this equation, and we get that the change of output voltage over time is equal to VO over R C. Now we want to find A and B in this state model. So we can try to substitute the values that we have with the states and the input of the state space model. So we therefore have the derivative of the current is equal to 1 over L multiplied by U. And if we look at this equation, we see that we have R and C, which are constants, and we have VO, which is a part of X. So we can write this as 0, 1 over RC, and then multiplied by X. Now X dot is just the derivative of the current and the derivative of the voltage. So if we put these equations here in here, we will get X dot is equal to, if we first look at this equation, we can see that we don't have any X, which means that we would just have zeros here. So in this matrix, multiply by X, and then plus 1 over L in this matrix, multiplied by U. And now if we look at this equation here, we can see that we have the X. So we just put in what's in front of the X, multiplied by RC, 1 over RC, and we don't have any U, so we just write 0. We therefore get that this is A on, and this is B on. Now we'll do this one a little bit faster because it's basically the same. So when it's off, we know that the voltage over the inductor L is equal to VI minus VO. So here the change of current in the inductor is equal to VI minus VO over L. So yeah, the VO is time variant, so I write a lowercase v. So because the MOSFET is off, all of the current going through the inductor is going through the diode as well over to this side of the boost converter. So the conductor current is equal to the capacitor current plus the current on the output side. So IL is equal to IC plus IO, which means that IC is equal to IL minus IO, and this one is equal to VO over R, just like last time. So now if we put IC into this equation, we get IL over C minus VO over RC. So if we rewrite the equations with these variables, we get, so if we just split this one into two parts, so we first have VI, which is equal to U, so U over L. And then we have plus, even though it's minus, but we say plus, multiplied by X multiplied by a matrix. So if we look at the X here, we know that we want the VO. And we don't want the IL, so we put a 0 first. And we multiply VO by minus 1 over L. So we get this equation. And now we can do the same for this. So we have 1 over C multiplied by IL, which is in the X here. And we don't have any VO, or we do have VO. So we write minus 1 over RC, and then we multiply by X. We have that X dot is equal to, so we first consider this equation. So we just swap places with this one and this one. So we have 0 and then minus 1 over L. And this is the first matrix, so we multiply by X. And then we have plus 1 over L. Then multiply by U. And then we consider this equation. So we have 1 over C, and then minus 1 over RC. And here we have 0. So we get that this is A off, and this is B off. And we can actually use these two matrices that we've just found to find a new matrix. Now we have two different state space models, but we actually just want one. So we can do an approximation to find A and B for the state space model for the whole boost converter. So what we want to do is actually to just add these two together. So the idea is that the MOSFET is turning on and off. So when it's on, we use this state space model. And when it's off, we use this state space model. So if we just add the two state space models together and multiply this one with D and this one with 1 minus D, we will actually get another state space model. So we have the real state space model is equal to D multiplied by the state space model when it's on, and then plus 1 minus D multiplied by the state space model when it's off. I now see that I forgot something on A on. I forgot A minus here, and if you look back, you will understand why. So this is equal to D multiplied by A on plus 1 minus D multiplied by A off. And we do the same for the B matrix. I forgot the X, though. And if you look at the B matrices, you can see that they are the same. So we don't need to do a approximation for them. So we can just write the B matrix. So we can just write BU here. So now where B is equal to B on is equal to B off. Now to make it easier, we would substitute 1 minus D with D prime. So now we can just add these two matrices together because we have X in both of the terms. So we still have 0 in the top left. And there's nothing here. So we can just write this one in the top right. So we have D prime over L, and we also need to remember the minus sign. And we can do the same for 1 over C, because there's 0 here as well. So we have D prime over C. And now we can see that the lower right value is the same in both of the matrices, which means that we can just write the value down. And then we multiply by the X, and we add the B matrix as well, and multiply by U. So you can see that this is now the A matrix, and this is the B matrix. So this is the state space model for the boost converter. But the problem is that if we want to control the boost converter, we want to be able to change the duty cycle of the MOSFET. So therefore, we can't use this state space model. We need to add another variable. And therefore, we can linearize around the equilibrium point of this state space model. So just rewrote the A matrix, so we have 1 minus D because we need that now. So now we want to linearize this state space model. So we have the derivative of x dot with respect to the duty cycle. So we know that we can just ignore this B matrix because it doesn't have any duty cycle. And then we just take the derivative of the A matrix with respect to the duty cycle. So we have that here and here. So we already know that this part remains 0 and this part remains 0. So we can just write that. So we have 0 here and 0 here. So if we take the derivative of this part, we actually get 1 over L, because this constant here, this 1, will disappear, and we just take the derivative of the D. And this part will be almost the same. It will be 1 over C. And then we still want to multiply by X. So if we now multiply this matrix by X, we get VO over L, and then IL over C. I forgot the equal sign there. But these are dependent on the states, which we don't want. So when we're linearizing around the equilibrium point, which means that we can substitute the VO and IL for some constants. We know that the gain of the boost converter, VO over VI, is equal to 1 minus D, or 1 over 1 minus D. And yeah, actually now these are constants, so we can just write with a uppercase and then a large I here. Yeah, so this is the case. So therefore, we have that VO is equal to VI over 1 minus D, or VI over D prime. We can actually do a pretty similar thing for IL. So with the power balance, we know that IL multiplied by VI is equal to VO multiplied by IO, right? So IL is therefore equal to VO over VI. And we know that IO is equal to VO over R. So VO over R. So we can actually just put this equation into here, and we have VI over R, and then D prime to square. If we now put these equations here into this, we will get first VO over L D prime. I mean VI, and then we have, for the lower part, VI over RC. Now we have D prime squared. So we just found this now. So we can find the new state space model simply by adding this multiplied by the duty cycle, the real-time duty cycle. And the D that is in A is the equilibrium D. So now this is all we need. So we can just add this part. So this matrix multiplied by D, the duty cycle. So we have VI over L D prime. And then we have VI over RC. And then D prime squared. So this is the matrix. And then we multiply by the duty cycle, the real-time duty cycle. And the D here is the D in the equilibrium point of the state space model. So the D we find by using the gain of the boost converter. And in order to control the output voltage, we can just adjust this duty cycle here in order to adjust VO. And U and VI is not the same either, because VI here is the equilibrium point of the state space model, and the U is the real-time value of VI. Because when we linearized, in order to get this matrix, we linearized around a equilibrium point. So every value in this matrix here is constant. And the same applies for this matrix, the A matrix.